Adding an additional ground wire in the base of a light pole is essential for several reasons. The primary benefits include enhanced safety. Ground wires provide a low-resistance path for electrical currents to travel to the earth. This reduces the risk of electrical shocks and fires if there is a fault or lightning strike. Another crucial reason is lightning protection. The extra ground wire helps dissipate lightning energy more effectively, which protects the light pole and its electrical components from damage. Code compliance is also a key factor. The National Electrical Code (NEC) often mandates the use of an additional ground wire for light poles under specific conditions. This includes situations where the light pole is in an area with high lightning activity or if it exceeds a certain height, often 20 feet. The term unencased ground wire refers to a ground wire that is not enclosed within a conduit or other type of protective covering. These wires are typically made of stranded copper or galvanized steel. During installation, the unencased ground wire is placed directly below the light pole, usually buried in the ground. The necessary length of the unencased ground wire will depend on the specific soil conditions and the local code requirements in your area. However, in most cases, 15 feet of unencased ground wire is generally sufficient for typical applications. When installing an additional ground wire in the base of a light pole, you should follow these procedures carefully. Firstly, dig a trench that is at least 2 feet deep around the base of the light pole. Secondly, carefully place the unencased ground wire into the trench you've dug and connect it securely to the ground terminal located in the light pole. Thirdly, backfill the trench with a conductive material. Crushed rock or gravel are suitable choices for this purpose. Make sure the material is packed firmly to ensure good contact. Seal the trench to protect the connection. Fourthly, be sure that the ground wire extends at least 5 feet beyond the base of the light pole and is driven securely into the earth. By adhering to these installation guidelines, you can significantly enhance the safety and overall reliability of your light pole installation. Let's delve into the specifics of grounding and bonding as it relates to light poles, emphasizing the importance of each aspect for safety and code compliance. Grounding, in the context of electrical systems, refers to creating a low-impedance path from electrical equipment to the earth. This path allows fault currents to flow safely back to the source, causing overcurrent protective devices such as circuit breakers or fuses to trip and to energize the circuit. In the case of a light pole, proper grounding ensures that if a live wire comes into contact with the metal pole, the resulting fault current will quickly trip the breaker, preventing the pole from becoming energized and posing a shock hazard. The National Electrical Code (NEC) Section 250 provides comprehensive requirements for grounding and bonding. Specific sections such as 250.50 through 250.68 detail the methods and requirements for grounding electrodes, which are the means by which the electrical system is connected to the earth. Common grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes, often referred to as UFA grounds. For light poles, a ground rod is a typical choice, supplemented by the unencased ground wire as described earlier. The size of the grounding electrode conductor, which connects the equipment grounding conductor to the grounding electrode, is determined by NEC Table 250.66, based on the size of the ungrounded conductors feeding the light pole. Bonding, on the other hand, involves connecting all metal parts of an electrical system together to create an electrically conductive path. This includes metal conduits, enclosures, and equipment frames. The purpose of bonding is to ensure that all these metal parts are at the same electrical potential. If a fault occurs, this minimizes the voltage difference between different metal parts, reducing the risk of electric shock to anyone who might come into contact with them. NEC Section 250.92 specifies the requirements for bonding service equipment, while 250.96 covers bonding other enclosures. In a light pole installation, bonding is achieved by connecting the metal pole itself to the equipment grounding conductor, which runs back to the electrical panel. This connection ensures that the pole is at the same potential as the grounding system, minimizing shock hazards. The equipment grounding conductor size is determined by NEC Table 250.122, based on the rating of the overcurrent protective device. The unencased ground wire, buried in the ground, serves as a supplemental grounding electrode. It provides an additional path to ground, further reducing the impedance of the grounding system. This is particularly important in areas with poor soil conductivity, where a single ground rod may not provide a sufficiently low impedance path to ground. The 15-foot unencased ground wire provides a larger surface area in contact with the earth, improving the overall grounding effectiveness. The depth of the trench for the unencased ground wire, typically 2 feet, is important for several reasons. Firstly, it places the wire below the frost line in many climates, preventing it from being heaved out of the ground by freezing and thawing cycles. Secondly, it provides a more stable and consistent soil moisture content, which improves the conductivity of the soil. Thirdly, it protects the wire from accidental damage during surface activities. The use of conductive materials such as crushed rock or gravel to backfill the trench around the unencased ground wire is also important. These materials help to maintain good contact between the wire and the surrounding soil, ensuring a low impedance path to ground. It is crucial to avoid using materials that are not conductive or that may corrode the wire. The requirement for the ground wire to extend at least 5 feet beyond the base of the light pole and be driven into the earth further enhances the grounding effectiveness. This extension provides a longer path for fault currents to dissipate into the earth, reducing the potential for voltage gradients around the light pole. It also helps to ensure that the ground wire is in contact with undisturbed soil, which typically has better conductivity than disturbed soil. In areas with high lightning activity, additional measures may be required to protect light poles from lightning strikes. This may include the use of lightning rods or surge protective devices, SPDs, installed at the base of the pole. Lightning rods provide a preferred path for lightning to strike, diverting the energy away from the electrical components. SPD protect against transient voltage surges caused by lightning or other electrical disturbances. These devices clamp the voltage to a safe level, preventing damage to sensitive equipment. NEC Section 280 provides requirements for surge protection. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. This includes visually inspecting the ground wires and connections for corrosion or damage, and using a ground resistance tester to measure the impedance of the grounding system. Any deficiencies should be promptly corrected to maintain the safety and reliability of the light pole installation. In summary, the addition of an unencased ground wire in the base of a light pole is a critical safety measure that enhances grounding and lightning protection, ensures code compliance, and minimizes the risk of electrical shocks and fires. Proper installation and maintenance of the grounding system are essential to ensure its continued effectiveness. When working with electrical systems, always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. Let's consider some real-world scenarios where the presence of a properly installed ground wire in a light pole can make a significant difference. Firstly, imagine a situation where a vehicle accidentally strikes a light pole, damaging the internal wiring. If the hot wire comes into contact with the metal pole, the presence of a low impedance ground path will immediately cause a large fault current to flow. This high current will trip the circuit breaker, de-energizing the circuit and preventing the pole from becoming electrified. Without a proper ground wire, the pole could remain energized, posing a serious shock hazard to anyone who comes into contact with it. Secondly, consider a scenario where a lightning strike occurs near a light pole. Lightning strikes can induce large voltage surges in electrical systems, potentially damaging equipment and causing fires. A properly installed ground wire provides a path for the lightning energy to dissipate into the earth, protecting the light pole and its electrical components from damage. In the absence of a good ground connection, the lightning surge could travel through the wiring, damaging the ballast, the lamp, and other components. Thirdly, think about a situation where there is gradual degradation of the wire insulation inside the light pole due to age or environmental factors. Over time, the insulation may crack or wear away, exposing the bare conductor. If the exposed conductor comes into contact with the metal pole, the ground wire will provide a path for the fault current to flow, tripping the breaker and preventing a shock hazard. Without the ground wire, the pole could become gradually energized over time, making it difficult to detect the problem until someone receives a shock. Let's also examine the specific requirements of the National Electrical Code, NEC, as they relate to grounding light poles. NEC Section 410.30 generally requires that metal poles supporting luminaires be grounded. This section references Section 250 for the specific grounding methods. Section 250.45 emphasizes the importance of effective grounding paths, stating that electrical equipment must be installed in a manner that creates a low-impedance circuit facilitating the operation of overcurrent devices. Section 250.50 details the requirements for grounding electrode systems, which must be connected together to form a single grounding electrode system. This ensures that all grounding electrodes are working together to provide a low-impedance path to ground. Section 250.52 specifies the types of grounding electrodes that are permitted, including ground rods, metal underground water pipes, and concrete encased electrodes. Section 250.66 provides the requirements for the size of the grounding electrode conductor, which connects the equipment grounding conductor to the grounding electrode. The size of this conductor is based on the size of the ungrounded conductors feeding the light pole. Section 250.122 specifies the requirements for the size of the equipment grounding conductor, which runs from the electrical panel to the light pole. The size of this conductor is based on the rating of the overcurrent protective device. It's important to note that local codes may have additional requirements for grounding light poles, so it's always essential to consult with the local authority having jurisdiction, OJ, to ensure compliance. In addition to the NEC requirements, there are also industry best practices for grounding light poles. These include using corrosion-resistant materials for ground wires and connections, protecting ground wires from physical damage, and regularly inspecting and testing the grounding system. It's also important to ensure that the soil around the ground wire is properly compacted to maintain good contact with the earth. In areas with poor soil conductivity, it may be necessary to use multiple ground rods or chemical ground rods to improve the grounding effectiveness. Chemical ground rods contain chemicals that leach into the soil, improving its conductivity. When installing a ground wire, it's crucial to make sure that all connections are tight and secure. Loose connections can create a high-resistance path, reducing the effectiveness of the grounding system. It's also important to avoid creating ground loops, which can cause noise and interference in electrical systems. A ground loop occurs when there are multiple paths to ground, creating a circulating current. To prevent ground loops, it's best to ground all equipment to a single point. Let's now look at the specific steps involved in installing an unencased ground wire in a light pole. Firstly, you'll need to dig a trench around the base of the light pole. The trench should be at least 2 feet deep and wide enough to accommodate the ground wire. Secondly, prepare the unencased ground wire. This typically involves stripping the insulation from the end of the wire and attaching a grounding lug. Thirdly, connect the ground wire to the ground terminal on the light pole. This terminal is usually located inside the pole's base. Fourthly, place the unencased ground wire in the trench, making sure that it extends at least 5 feet beyond the base of the light pole. Fifthly, backfill the trench with conductive material, such as crushed rock or gravel. Make sure the material is properly compacted. Sixthly, drive the end of the ground wire into the earth. This can be done using a ground rod driver. Seventhly, test the grounding system to ensure that it's working properly. This can be done using a ground resistance tester. Finally, document the installation, including the date, the location of the ground wire, and the test results. This documentation can be useful for future maintenance and troubleshooting. By following these steps, you can ensure that the unencased ground wire is properly installed and that the light pole is adequately grounded. Remember, safety is always the top priority when working with electrical systems. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns.